Welcome to this presentation on data block size and replication factor in the Hadoop Distributed File System, or HDFS. In this session, we will explore how these two core parameters impact system performance, storage efficiency, and fault tolerance. Whether you're tuning an HDFS cluster or designing a data-intensive application, understanding these factors is key. Let's begin with the concept of data block size. In HDFS, files are not stored as single units. Instead, they're split into fixed-size blocks, typically 128 megabytes by default. This block-based approach is fundamental to HDFS design. Larger blocks help reduce disk seek overhead, boosting throughput especially during large sequential reads. From a metadata perspective, fewer blocks mean fewer entries to track in the name node's memory, enhancing efficiency. Furthermore, block-based storage enables parallel data processing. Tools like MapReduce or Apache Spark can operate on multiple blocks concurrently. Now, let's examine how block size affects system performance. When you choose smaller block sizes, you increase metadata overhead. However, it helps reduce internal fragmentation, which is beneficial for storing many small files. On the other hand, larger block sizes improve sequential I/O performance and are much more efficient for handling large data sets. When designing a system, remember, small files benefit from small blocks, while large-scale data analytics require large blocks for better performance. Next, let's define the replication factor, often abbreviated as RF. In HDFS, each data block is stored in multiple copies across the cluster. By default, the replication factor is 3, meaning each block exists on 3 different nodes. This provides fault tolerance, allowing the system to withstand up to 2 simultaneous node failures without losing data. It also enhances data locality. Computation tasks can be scheduled on nodes that already host the required data block. Plus, it supports rescalability. Since multiple replicas exist, concurrent read requests can be distributed across nodes for faster response. What happened when you changed the replication factor? A low replication factor, such as 1, speeds up writes and saves storage costs, but at the expense of durability. Conversely, a high replication factor, say 5, increases storage consumption and slows down writes but significantly enhances fault tolerance. For system design, it's essential to strike the right balance. Use higher replication for critical data sets and lower replication for test or temporary data where durability is less important. Let's now explore how block size and replication factor interact. Larger block sizes mean fewer disk seeks and faster scan speeds, ideal for analytical workloads. However, a higher replication factor can introduce write latency, since more nodes are involved in the process. That said, it also enables faster parallel reads, since more copies are available. From a storage perspective, increasing the replication factor means increasing storage cost. For example, using a replication factor of 3 results in 200% overhead. Each block is stored 3 times. Fault tolerance is at the heart of HDFS design. With a replication factor of 3, HDFS can survive both a node failure and a rack-level failure. HDFS includes automatic rebalancing, which ensures that lost or under-replicated blocks are restored without manual intervention. As a best practice, it's advisable to use block sizes in the range of 128 to 256 megabytes for analytics workloads. Avoid using blocks smaller than 64 megabytes, as they generate excessive metadata that can overwhelm the name node. Choosing the right replication factor depends on workload requirements. Use a replication factor of 3 for standard, balanced workloads. For ultra-critical data sets where downtime or data loss is unacceptable, increase it to 5 or more. For non-critical, short-lived, or test data, you can reduce it to 1 to conserve resources. To further optimize storage, consider using erasure coding, a method that provides fault tolerance with less overhead. Compared to replication, erasure coding can save up to 50% in storage cost while maintaining durability. Let's look under the hood at how HDFS handles data replication. When a client writes data, it initiates a write pipeline. The data is first sent to the first replica, which then forwards it to the second, and finally to the third. HDFS also supports rack awareness. This means replicas are intelligently distributed across different racks, typically 2 replicas in one rack and 1 in another, to protect against rack-level failures. The name node keeps track of all blocks and their locations. Note, higher replication factors mean the name node must track more metadata, requiring more memory. To summarize, Block size determines the speed of data input and output, as well as the amount of metadata the name node must manage. Replication factor dictates the level of fault tolerance, the ability to scale reads, and the overall storage cost. General guidelines include: use large blocks to maximize throughput, maintain a replication factor of 3 or more for resilience, and consider erasure coding when you want fault tolerance with lower storage overhead. Understanding these parameters allows you to design and tune your HDFS cluster for maximum performance and reliability.